Hi, welcome to today's lesson. Today we're going to be talking about curve sketching, specifically how to find local maximum points, local minimum points, stationary points of inflection, and non-stationary points of inflection. Then we're going to put it all together at the end, talk about how to graph all these things. I hope you enjoyed today's lesson. Let's talk about curve sketching. For an increasing function, the graph rises from left to right. For example, if x2 here is greater than x1 here, then the function value at x2, or f of x2, will be greater than f of x1. That's for an increasing function. x2 greater than x1, then the function value of x2 will be greater than the function value at x1. That's an increasing function. For a decreasing function, the graph decreases from left to right. If x2 is greater than x1, then the function value at x2 is less than the function value at x1. So here we have x2 is greater than x1, and we see that the function value at x2 is less than the function value at x1. We're comparing the y values. This is lower than this, so f of x2 is less than f of x1. Let's talk a little more about curve sketching. Here you see I've drawn a graph, we'll call it f of x. And the graph goes up and down and up again. And I've split the graph into sections A, B, C, and D. In this section, where x is in the A region, any tangent will have a positive gradient. If I draw a tangent here, it's going to have a positive gradient. So we see that dy dx is going to be positive for any point in this region to the left of this first vertical line. The function is therefore increasing. What you need to do is associate increasing function with a positive derivative. In this zone B here, from this vertical line to this vertical line, we've got any tangent has a negative gradient. So our dy dx, our derivative, is going to be less than 0 or negative, and from here to here our function is decreasing. Where x is equal to d in this region here, any tangent will have a positive gradient. Again, we see the gradient of the line is positive, the slope is positive, so dy dx, the derivative, is greater than 0 or it's positive, and the function is increasing. In our next example, we're going to be talking about these points here, where the function is neither increasing or decreasing. We're here talking a little more about curve sketching, and one of the most important things about curve sketching is to know where are the stationary points. The first thing we have to know when we're talking about stationary points is, what are stationary points? Well, stationary points are points where the function changes from increasing to derivative equals to 0 to decreasing, which is their derivative is less than 0. We call that a local maximum. You can see here the derivatives would be increasing, greater than 0, equal to 0, horizontal lines, and then decreasing. That's a stationary point, and that's called a local maximum. Also, we can have points where the function changes from decreasing, f dash of x is less than 0, to f dash of x is equal to 0, to increasing, which is f dash of x is greater than 0. We see here the derivative is negative, it's 0, and then it's positive. That's what a local minimum is. So, stationary points are really any time you have f dash of x is equal to 0, you're going to have a stationary point. We can have local maximums have a stationary point, and local minimums also have a stationary point. Also, don't forget, we've got stationary points at something called the stationary point of inflection. We'll see that on our next slide. So in summary, what you need to remember about stationary points is that we've got three types of stationary points. We have local maximums. The derivative at the maximum is 0. F dash of x is equal to 0 at that maximum. It has a horizontal tangent line. The local minimum also has a horizontal tangent line, meaning the slope of that tangent line, or another way to say it, is the derivative at this point is equal to 0. And the last type of stationary point is a stationary point of inflection. Notice the derivative here is positive, 0 to positive. And here we go, negative to 0 to negative. Both of these are points of inflection. Local max, local min, and stationary point of inflection. Those are the three types of stationary points. When we set the derivative equal to 0, we're checking out to see if we've got a local max, local min, or a stationary point of inflection, increasing or decreasing. Let's now take a closer look at our first stationary point. Remember, these are all stationary points. We've got maximums, minimums, and stationary points of inflection. Our first one is a local maximum. Very carefully look at the labeling of the axes here. We've got a y-axis versus an x-axis. So this is our original curve. This would be f of x. The original curve is labeled f of x. And here I went over x1 on the x-axis. So our point is x1, y1. So this would be y1. We're over x1, up y1. At x1, we can see that we have a horizontal tangent line. So we'd say that f dash of x1 is equal to 0. That's what a stationary point is. By definition, we have derivative 0 at a stationary point. Now, why is this a maximum? For x is less than x1, so we're in this region, then f dash of any x in that region is greater than 0. Our tangent lines are going to have positive slopes. For x is greater than x1, so in this region here, then our derivative, f dash of x, is going to be negative. We're going to have lines that slope down like this that meet our curve at just one point. Our tangents will have negative slopes. Well, what does this mean for our new set of axes, which is dy dx? That's the derivative versus x. Well, our derivatives are positive to 0 to negative. Our derivatives are positive to 0 to negative. So we can see that a line like this is a good representation of what's happening to the slopes of our tangents, the derivative. We're graphing the derivative, dy dx, against x. And our derivatives went positive, so I'm above this x-axis. These are all positive values for our derivative. Then we go to 0. Well, here is our dy dx, and we go to 0 at this point here. And then for values greater than x1, our derivatives are negative, so they're down below the x-axis. If we talk about a sign diagram for the first derivative, it would look like this. It went from positive to 0 to negative, so we'd say dy dx looks like this. To let you know that if we're looking at the derivative, it went from positive to 0 to negative, that must be a maximum. Don't forget, a maxima is just one of 3 types of stationary points. And every time we have a stationary point, f dash of x is equal to 0. Now let's talk about our second stationary point, the local minimum. Here is our graph. Again, very carefully look at the axes. This is y versus x. So our point x1, y1 is right there. Well, if this is our curve on the xy axis, this is then our function f of x. At this point, we have a minimum point. So we can see here, our tangent line will be horizontal. That's what stationary points are. At x1, our f dash of x is equal to 0. Now for any x in this region, to the left of x1, for x is less than x1, we can see that we're going to have negative slopes for our tangents. So we say that f dash of x is less than 0. For x is greater than x1, our tangent lines will be positive. So for x is greater than x1, our f dash of x, our derivative, will be positive. And we're increasing as we increase x away from our minimum point. Well, what does that mean if we're going to try to graph our derivative? Look at, now it's no longer just y, it's dy dx versus x. Our derivatives went from negative to 0 to positive. From negative to 0 to positive. Well, a good representation of that is a line that looks like this. This shows how the derivative is changing. It went from negative, below the x-axis, to 0, right at the x-axis, to positive. We are graphing the derivative. How does this look in a sign diagram of the first derivative? It'd be something like this. And we're showing that this is dy dx went from negative to 0 to positive. Again, this is a type of stationary point. We have 3. We have maximums, minimums, and stationary points of inflection. At each stationary point, f dash of x is equal to 0. We have a horizontal tangent line. Let's now talk about stationary points of inflection. You can see it's a stationary point, which automatically you should be thinking, well, f dash of x equals 0. I must be dealing with horizontal tangents. And again, we are. Check out this point, x1. Look at what happens to our tangent as we go to x1. We're going to have a horizontal tangent there, and also x2. We're going to have a horizontal tangent. Well, that means our derivative, which we're going to graph here, our derivative is 0. So we'll definitely have a point 0 there, and our derivative there is 0. Well, let's check out what's happening around these points of interest, x1 and x2. At x1, our derivative is 0. For x is less than x1, so in this region here, we can see, well, let's take a look. What do the tangent lines look like when x is less than x1? They're all positive. So we can say for x is less than x1, then our derivative is greater than 0. Well, how about if we leave x1 on the positive side, and let's take a look at the derivatives there. Well, our derivatives, again, will be positive. So we can see that the derivatives on either side of the point in question will be positive to 0 to positive. Well, what does that look like if we're going to graph dy dx? It's going to go from positive to 0 to positive. Positive to 0 to positive. We will have a graph that looks like this. Notice the point here, the stationary point, becomes a 0 on the graph of the derivative. Similarly, we've already established that if we're going down the hill like this, our derivative at x2 is 0. There it is. It's got a tangent line that's horizontal. Well, so at x2, f dash of x is equal to 0. By definition, that makes it a stationary point. For x is less than x2, we've got tangent lines that are going down. Our slopes are down, so they are negative. For x is greater than x2, again, we see negative tangent lines. So we're also less than 0 for our derivatives. Well, I know I have to go negative, 0, negative for my derivative. Negative, 0, negative. So a graph of the derivative is going to look something like that. We can make a statement about stationary points of inflection. F dash of x is equal to 0 for the stationary point of inflection. Now let's take a look at dy dx. If we derive this, if we took the derivative of this and graphed this, notice at this point here we'd have a tangent line that's horizontal. At this point here we'd have a tangent line that's horizontal. That would mean our derivative of our derivative will also be 0 at that point. That's what we call the second derivative. And that's also equal to 0. So you have to know this. For a stationary point of inflection, we have f dash of x equal to 0 and f double dash of x equal to 0. Both the first and the second derivative are equal to 0 at a stationary point of inflection.